Okay, good morning. So last week we have already discussed to able to dealing with a large number of particles. So we are interested only in the statistical behavior of the group as a whole rather than the individual behavior, rather than the behavior of individual particles. That's why that we have to introduce statistics laws here. So in general, there's three statistics laws. The first one is Maxwell-Boltzmann probability function, and the equation is shown me here. This is the considering the particles are considered to be distinguishable by being number with no limit to the number of particles allowed in each energy state. So this is for the case of the gas molecules. And second one is Fermi-Dirac probability function. This is the one which is much important for us. So this considers the case that the particles are again indistinguishable, but now only one particle is permitted in each quantum state. So that's exactly fit for our case. And for example, the application for this probability function that can be used for the electrons in crystal. And also there will be the third one called the Bosch-Einstein function. So that's the case used to describe that the particles are indistinguishable and there's no limit to the number of particles permitted in each quantum state. And this is equation mainly used for the photons. So in sum, so we will mainly use the Fermi-Dirac probability density function for the later discussions. So here is something more related, details related to the Fermi-Dirac probability function. We have the several terms is defined here. The first one is the number density, Ne. So the Ne is the number of particles per unit volume per unit energy. And second one, the Ge, function Ge, is number of quantum state per unit volume per unit energy here. So therefore, the Fermi-Dirac Fermi-Dirac distribution is defined by the Ne over Ge, and the Ne is actually means the number of the particle. And Ge is a number of a quantum state. So the concept is also very simple, just like the case that we have a number of the seats and then we have a number of the student here. So the probability of the student in this class just number of students over the number of seats. So that's the same like in this one, that we have a number of particles over number of a quantum state. So that's our probability distribution function. And this is also called the FFE, that Fermi-Dirac distribution is equal to 1 over 1 plus exponential E minus EF over KT. And where the energy EF is called the Fermi energy. So let's just look at some of the case, like if we put in some number inside this Fermi-Dirac distribution function, let's see that how the plot will look like. So for example, if we consider the case of t equal to 0k, and if we consider the case when our energy is smaller than EF, so the exponential E minus EF over KT will approach to the exponential minus infinity here. So because this is smaller, it's become negative. So you will approach to minus infinity, and because the t is equal to 0. And that's equal to the 0 here. And therefore, the general form for the Fermi-Dirac distribution will be simplified if we consider energy is smaller than EF. And this one will become 1 here, because this one is equal to 0. So therefore, we can start to look at how this the plot look like. So this is a case with a y-axis as a Fermi FFE, and then the x-axis is energy. So if we assume this is a case of a t equal to 0k, and if the energy is smaller than our EF, the probability is equal to 1. So that would be exactly here. So on the other hand, if we consider the energy E larger than EF here, so this term will become exponential positive infinity. In the end, it's approach to the infinity here. And therefore, since this becomes infinity, and this term is very large, so this term in the end will become like it's 0. And therefore, we can understand in the case when E larger than EF region, our FFE is equal to 0. So our FFE is equal to 0 here. So therefore, with considering extreme case that the t equal to 0k, and with certain assumption, so we can derive for this and this region. And of course, in the middle part, that will be the case energy equal to EF here. And in this case, we will have the 1/2 half. So therefore, so finally, we can completely this plot with considering all three cases. So the basic idea for Fermi-Dirac probability function under the t equal to 0k is just like the function like here. That means when energy is below EF, the probability is equal to 1. But when the energy larger than EF, that's equal to 0. And in the middle, that's equal to the 1/2. So that gives us somehow certain idea that how this probability density function looks like. Of course, in reality, it's never to be possible to have the t equal to 0k. So that means there's always slightly change for this curve. So the next one is we try to understand that how this Fermi-Dirac probability function in the case when t is larger than 0k. So for example, right now, if we assume that system contains 13 electrons here. And the Fermi energy must be above E4 but less than E5. So that means our EF is here. So that's the EF here. So we can see that the electrons are in the lowest possible energy state, so that all states below EF are filled. So if you look at this schematic, also the energy state below EF are filled with all of the electrons here, and then all states above EF are empty. And therefore, we can start to consider to draw this with another way. So if you try to consider this is energy approach to EF. So this is you can still imagine that this is energy. We have the E1, E2, EF, E4 here. So we can consider replot the following. The left-hand figure is the right-hand side. That we consider the x-axis is the energy with respect to the Fermi energy, and then the y-axis can be the GE of NE here, and therefore the left plot can be redrawn as a right plot, that this region is a region that energy below EF. If you look at this schematic, when the electrons stay in the energy below EF, that is all the energy state are all filled. So that's exactly the same. This is a region where energy below EF. Therefore, all the energy state are all filled here. And on the other hand, the region like here can be referred to here as well, because this is a region that energy larger than EF, and it's supposed this is the energy state are all empty, and this part here. By the way, the GE here can be referred to this one. Density of allowed energy state in the conduction band. So that's a GCE. So this is exactly as shown me here. This is GE. Is a density of allowed energy state. Or it's the same like the previous one has mentioned, the number of a quantum state. So in general, just to describe that how many available states. So the GE is described. Maybe I can rephrase this as so that can be much easy for the understanding. So the GE is general considered as a available energy state. So this is still in the case of a t equal to 0k. So when t equal to 0k, all these electrons, they don't get additional energy, so there is a very stay in this region because they don't have any additional energy. But if in considering the case in the situation when the temperature increase above, so that means temperature is larger than 0k here. So electron can gain a certain amount of the thermal energy. So we will have the thermal energy that electron can gain, and therefore some electron can jump to the higher energy levels, and which means the distribution of electron among the available energy state will change here. So some of you can see from here energy state will change. So now you can see because of the some of the electron get some energy, so this electron will start to jump above our EF, and this is our EF. This is our EF here, and because of this thermal energy, so the electron will gain some energy, so you will be start to jump over this EF here. So the change in the electron distribution among energy level for temperature larger than 0k can be seen by also if we replotting again the Fermi-Dirac distribution here. So if we look at this plot here, so we all know from previous discussions already indicate that this is a case of t equal to 0k. But if we found out that there's a different temperature, for example T2 larger than T1, larger than 0k here, and there is a change for this plot as well. So then if this is a case of a T1, that will become like in this way. This is a T1. But if we have a T2, so that's a T2 here. So as you can see, as temperature increase, actually the probability density function also will be changed as well. The probability of energy about EF being occupied increase. As a temperature increase. So if you try to look at this plot in detail, you can also aware that actually this plot is also pretty consistent with the left-hand side. So if you consider left-hand side, let's assume there are some electrons can occupy in the region that energy larger than EF, and this is also indicate the same thing. There are some probability that electron can exist in the region where energy larger than EF. In the case of 0k, this is always equal to 0, so that means all the electron has no chance occupy in this region. But the temperature increase, actually the electron get a higher chance to occupy in this region. So that's exactly this sentence mentioned. The probability of energy about EF being occupied increase as the temperature increase. and the probability of state below EF being empty increase, the temperature increase. So that means you can see this is the empty of this electron state below EF is also increased because of this is decreased here. So this is some related information that when we have the temperature effect, because in reality, it's never too possible to have the case of T equal to 0K. So therefore, once we increase temperature, then the electrons can have a chance to jump over the EF, and then you will see the electron can occupy in this region. But that's also very consistent with the general consensus that if you already have a certain experience in the semiconductor device characterization, and it's well known that when you heat in your samples in the high temperature, you always get a high leakage current. That's pretty much like the general behavior for all kinds of the device. So this can be very nice to be understood from the fundamental series here. That's why, although many like the electrical behavior can be easily understood or guessed in a very straightforward way. For example, high temperature, you get a high leakage current. But now we also have very solid series in here trying to support our guess that why the high temperature always leading to the high leakage current here. Okay, so also when we consider the Fermi-Dirac distribution, sometimes we will do some additional assumption here. And one of the assumptions is very often used is when we consider the E minus EF, which is larger than the KT here. And that's how we call this as a Maxwell-Boltzmann approximation. So by consider this equation, and once your E minus EF larger than KT, and therefore this equation can be rewritten as a exponential KT minus E minus EF here. And if you try to look at this approximation compared to the original Fermi-Dirac distribution, as I say, this is only applied in the case when E minus EF larger than KT. So therefore, which can be only fit very well in the region of E minus EF much larger than KT, and we can use Boltzmann approximation. And later on, we will also use this one to simplify our calculation, and that can still give us a pretty nice understanding. So here's a summary for this the chapter. So first of all, describe allow energy state split into the band of allow energy state. So that's the very important concept that there's the band, and also the concept of the allow forbidden energy band was developed. So in this chapter, it's mainly to describe that how come that from the beginning we talk about crystal, we talk about the atoms, and in the end we can start to transform this concept to the concept related to the band diagram here. And we also talk about the E versus the K diagram of silicon germanium oxide. And we also talk about there's a difference between the direct and indirect band gap semiconductor. And also the most important thing is that in dealing with a large number of electron and holes, so we must consider the static behavior of these particles here. So we have to introduce statistic mathematics here, try to understand that the general behavior of the large particles. And therefore, we start to apply the Fermi-Dirac probability function. And this is to describe the probability of the quantum state at the energy E of being occupied by electron. And also we define the Fermi energy here. And some of these definition is kind of, if you look at only on the text, it's very difficult to understand straightforward. For example, the allowed energy state being occupied, allowed energy state not being occupied, the probability of the quantum state, the probability of allowed energy state. These things sometimes we try to just try to understand from text is very difficult. So it's always good that we have to use a certain plots with a figure and plots that can give us a quite straightforward understanding. So, and the last, this one is definitely the most important part, because later on we also need to use these Fermi-Dirac probability density functions, try to help us to calculate the electron and hole concentrations. Okay, so we start to move for the next chapter. So finally, I think we all have the basic understand for the electrons and the holes, all the basic series, that all the basic tools we need, try to further to calculate the electron and hole concentration. So the main question for us is that in the end we need to understand how to estimate the electron and holes here. So, and first of all, we still consider the basic case, that's a semiconductor in equilibrium. So when we talk about the equilibrium, that means this is a case that we don't give any additional bias. We just purely consider that how the electron and holes in the piece of the semiconductor material, that we don't give additional bias, we don't give the additional field, we don't give the additional light. That's a pure consider a case under the equilibrium. And this is the most basic case. And for sure that the next one we will consider that the semiconductor in the non-equilibrium, but that will be the several chapters later. So we always start from the beginning. As I say, what actually we are interested in, although we talk about the quantum mechanics tell us that actually we cannot estimate the carriers in a very precise way. We can only estimate in the probability. And also we start to introduce a Fermi-Dirac distribution function, because that can also is a good statistic tool, allow us to estimate the general behavior of the whole bunch of the carrier here. But still question in our mind is that how do we precisely calculate the electron and hole concentration, or general as a carrier concentration. So equilibrium distribution of electron and holes can be considered as the following, that we have the NE. So that's equal to our GCE times our Fermi-Dirac distribution. And how this equation come out is actually also it's just another form from the previous Fermi-Dirac. If you just go back to the check the previous slide for the Fermi-Dirac distribution. So how we define this is defined as you have the NE over GE and is equal to FFE, right? So that's a definition for the Fermi-Dirac distribution, and where the NE is a number of the particles. We can say the carrier is the same, and the GE is a number of the quantum state. So therefore, this gives us a very straightforward estimation that if right now we are interested in number of carriers here, that is equal to your number of quantum state times your probability density function, and that will become our NE here. So that's we start from the same equation we already have from the last chapter, and now we are interested under the thermal equilibrium electron concentration. So the thermal equilibrium concentration can be expressed by N0 is equal to the integration of the GCE FFE dE, because right now we are trying to integrate all these distribution along our energy. So that's the N0 here, and the 0 here is actually mean this is a case for the thermal equilibrium. So in the later on, we will have very often to have this 0 in the somewhere. That's always suggests that this is a case under the equilibrium. And for electrons in the conduction band, we have E energy larger than the conduction band, and if EC minus EF larger than the KT, then E minus EF will also larger than the KT, and therefore we can start to apply the Boltzmann approximation where we just mentioned in the last chapter, and therefore this equation can be rewritten as here exponential KT minus E minus EF. So that's the Maxwell-Boltzmann approximation. And now the G0, is something we also have been shown in the last chapter. So right now what we are doing is just try to make this equation. We fill this one here, we fill this one here, and in the end this one will become like here. So therefore this N0, the full expression for this N0 is shown in here, and where this is GC and this is FFE. Okay, so although this equation looks a little bit scary because that looks complicated, but if you try to pay some attention and you look at in detail, found out this just exactly the same, and all the things component we mentioned here that's already mentioned previously. Okay, so finally we can start to think about that how to derive this equation, how to estimate our N0. That's thermal equilibrium electron concentration. And fortunately, I don't think we need to really derive in the mathematic way. We can also use a plot to give us a certain understanding of this calculation. So this is a equation that we already shown in previous slide. That's a thermal equilibrium electron concentration. And this P0, that means this is a whole concentration. So now we can use the plot way, try to give us a certain understanding. Again, we consider the case that as a Venn diagram. So inside the Venn diagram, as you know, it's always, this is a conduction band, and this is a valence band. And also, we already know that the distribution for the GC is look like in this way. So that's a GCE. And this is a GVE. And also, we have also defined inside somewhere between EC and EV, there's a term that we call the energy, Fermi energy. So now if we assume our Fermi energy just here, so that's a EF. So this EF is exactly the same that's mentioned here. The EF should be somewhere in between the band gap between the EC and EV. So now we assume our EF is just right in the middle here. And now also we all understand the distribution for the Fermi, based on the Fermi-Dirac distribution. If you look at this plot, this is FFE versus energy. Now actually we just try to change this graph as a vertically, because right now if you make this graph as a vertically with energy versus FFE, and how this graph will look like. This graph will become like here, like in this way, right? Just try to turn around in the 90 degrees, and therefore this is exactly the way we want to use, because our y-axis now is energy. So now this is energy, and this is our Fermi, our probability. So what I'm going to do is I'm trying to replot again this as a Fermi-Dirac distribution. So in the end, this will become like here. And this is a function of FFE. So don't feel surprised about this equation or this curve, because this just exactly the 90 degree turning around of this plot. Because if you change this one, let's say again, if you plot this E versus FFE, then you will get this same curve, and which is exactly this one. Okay, so again, don't be really confused by this equation, because of course, if you try to do the hand calculation, hand estimation of this equation with a very complicated integration, that's always very challenging. But now if we use the plotting way, and that can give us a pretty straightforward sense. And I have to just slightly revise for this curve, because that's more convenient for me. And therefore, now our question is still back to this term here. This integration of the GC times FFE. And GC is a blue one, which is this one. And the FFE is a red one here. So integration of this, in the end, just a integration of this plot, and actually just the product of this plot. That means just this one times this one, and from this graph, actually the product of these two curves, just the overlap region, So to have the more precise drawing, I try to make this overlap region as larger as possible. So then actually just this overlap region will become the integration result here. So now if you try to start to calculate the GC times FFE, that's equal to our NE here, and which is just an overlap region of this one, and that is equal to here. So the area of this is equal to our N0, and that's exactly the electron concentration. Okay, so finally, we can use this simple plot help us to solve this mathematical equation. So now we can get idea that actually this times this one is just this overlap region, and this overlap area will become our electron concentration. So the similar things, if we do the similar things for the holes as well, then actually the overlap region, but because here is 1 minus FFE here, but in general the idea is the same, that the overlap region of here GVE times 1 minus FFE, which is equal to our hole concentration. So the area shown in here is P0. So that's a hole concentration. Okay, so finally, we can all combine everything and in the Venn diagram, and that can give us a sense that how actually the electron concentration, how the whole concentration can be estimated. And of course, although we can understand from this plot now, and we understand that how the electron concentration is mainly determined by this Fermi-Dirac diffusion and also this allow energy stay here, but we still need to try to derive the equation here. Here's some more calculation here, but we won't go very detailed because that's just a further calculation from previous equation. But in anyhow here, the N0 can be calculated as shown here, and where NC is equal to this one, so this is NC, and then because in here he defined this one as NC, and therefore the NC will be mainly like the constant here, so therefore that's why we define another parameter as NC here. So the N0 is equal to NC exponential minus EC minus EF over KT here, and the name of NC is effective density state function in the conduction band here. So still, this equation of course is good for estimate the electron concentration, but actually the further physics-based implication is much more important than the equation shown here. But the understanding is very simple. Let's look at again for our band diagram here. So we have the EC, we have EV here, conduction band and valence band. So now in the previous slide, we assume our EF is just a line in the middle between EC and EV. But if now our EF is not in the middle, our EF is actually close to our EC, what actually this will suggest for us, and this suggestion and this physics-based implication is very important. It's way more important than the equation. So if right now the EF is close to the EC, so that means EC minus EF becomes smaller, right? So this difference becomes smaller. If this difference becomes smaller, and if you come back to look this equation, you can imagine that the exponential EC minus EF, this term become larger. Right? Because this is become smaller, and this is the minus exponential of this term, so this one become larger. So that means our electron concentration is larger, and that actually suggests that in this piece of the semiconductor material, we have the higher electron concentration larger than the whole concentration, and therefore this is N-type semiconductor. This is N-type semiconductor. So now, if you don't remember this one, that's fine. But the most important thing is finally, we can use the position of a Fermi energy to understand this material, whether it's N-type or P-type, or it's a highly concentration. The concentration is high or not, because as long as EF is close to the conduction band, that actually already suggests that this is N-type material. On the other hand, if our EF is close to our valence band, and that actually suggests this is a P-type semiconductor material. And that's very important because in the later on, the EF is a important indication that tells us that how higher the concentration is, and EF also later on will become the main key parameter that we are interested in, because that can determine the carrier concentration. Also, in the later on, will determine the certain band offset and the band barrier here. So that's finally we have reached the most important concept that we can use the EF to understand whether this is material is N-type or P-type. Although it takes several details related to the different equation, how this concept form. But now the conclusion, I think, is very simple compared to for the previous, all the details derived. This is same thing for the whole electrons. So in here we won't do the again, but it's also give us an idea that we can use the same way to estimate the whole concentration, and there's some like a typical parameter for the NC and NV that will be depends on our materials here. So the Fermi energy level for the intrinsic semiconductor is called the intrinsic Fermi energy. And in here, because this is the semiconductor in the equilibrium, and then in most of the case, we will first to discuss intrinsic carrier concentration. So intrinsic, it means that this is a semiconductor material that has exactly the same electron and the hole concentration. So that's a material what we call as the intrinsic semiconductor. So in the case of intrinsic semiconductor, our electron thermal equilibrium electron concentration, because N is also equal to P, and that's also equal to Ni here. And so this is N0 is equal to Ni is equal to Nc exponential and that's a case for the N0 equal to Ni, and then also N0 is also equal to this one. The same thing is here. The P0 is equal to Pi, but also Pi is also equal to the Ni, because this is a intrinsic semiconductor. equal to, but the Pi is also P0 is equal to NV exponential KT minus EFI minus EV here. By the way, because right now we consider for the intrinsic semiconductor, so that means our Fermi energy is equal to EFI here. So with these two equations here, we can try to also have the equation like Ni squared. That is exactly this times this one, which will be equal to this times this one, and now this NC NV will times together. So now you have the NC NV exponential EC minus EV over KT. Because right now, this times this one and EFI will be cancelled. So now you only have EC and EV left here. So then you have this one here. And also, this equation can further derive as a NC NV exponential the EC minus EV just exactly equal to the band gap. So that's equal to EG. So finally, as I say that sometimes the equations look scary, but the overall idea is because we want to have very simple physics-based concept. But now we back to our very simple conclusion. Again, here that this is intrinsic carrier concentration. It's a very strong function of the temperature and also band gap. As shown here. So that's very important because later on this also implies something for our semiconductor material property and device characteristic. So right now from this page, now we understand that our intrinsic carrier concentration here is strong function of our band gap and also the temperature. And here is some like the typical value for the Ni with the different semiconductor materials here. The most important one for sure is silicon. So the silicon, the Ni is 1.5 times 10 to 10 in this order. So that's a very important value for the silicon. But this value is need to be comparison with the other material, then you can get some a little bit sense here. And here I will prefer to refer to this graph here. So as I say, the intrinsic carrier concentration is a very strong function of the temperature. And therefore, from previous equation, we can know the Ni is equal to so that is equal to here. And we have a silicon band gap is 1.1 electron volt, so we can have the Ni as a function like here. The intrinsic carrier concentration is determined by the thermal generation of electron hole pairs across the energy band gap of the semiconductor. So that means this is the number to describe that if you have the EC, EV here, and we all know below the EV is a place full of the electrons here, and therefore intrinsic carrier concentration is determined by thermal generation of these electron hole pairs across this energy band gap of the semiconductor. And now if you try to plot this one formula, you can have these figures shown in right hand side. So this is intrinsic carrier concentration, this is temperature, but now we prefer to plot as 1000 over T here. So as 1000 over T, that means the left hand side is a low temperature. And then the right hand side is low temperature, and then the left hand side is a high temperature. But now if you look at this curve in detail, you'll find out that in the high temperature region, actually the carrier concentration is getting very high. And that means you have a lot of the electrons easily to cross over the band gap and reach to the conduction band. And that's also in the end is very consistent with our general understanding that if you put a piece of a material in the high temperature, if you measure the current, that gives us a very high current. So now that's also the same. So in the end, the purpose for this equation in the end just all consistent with the same estimation that we already have, that as long as with a high temperature, it's always that we got a higher leakage current here. So that's why to overcome this challenge here, then we can start to think about that what possible material that can give us a sense that to avoid that under the high temperature operation we have very high leakage current, because this is something that we don't want. That's why that in the beginning we mentioned that there's a material called the wide band gap material here. The idea for wide band gap material that's already mentioned before, but we can also use this simple equation to give us a certain idea. So again, the typical silicon material has a band gap around 1.1. This is a case of a silicon. We have a band gap around 1.1 electron volt, and that's the difference between the EC and EV. But now if we have a material that has a larger band gap, that has a larger than 3 electron volt here. For example, this can be the material of the silicon carbide. This can be material of the gallium nitride. And because this has a band gap which is 3 times larger than the silicon, so that's why generally we call this as a wide band gap semiconductor. But now, if you look back from this equation, if we have a material has a large band gap here, and this is minus exponential minus band gap, e.g. here, so means this increase, that means this will decrease. So that can fit for our purpose because we want to have a material has a low intrinsic carrier concentration. So therefore, if you look at this plot, this is intrinsic carrier concentration versus the temperature and maybe let me just rewrite, just write again for the equation. So the Ni is equal to this one exponential Eg over 2kT. So if now the band gap is larger, the term is here. And this is exactly how this graph tries to tell us. This is Ni. And this is a temperature. But now with respect to the different band gap material, silicon has a band gap 1.1 electron volt. Silicon carbide and gallium nitride has a band gap larger than 3 electron volt. So now you can see with a temperature around 800 K, these already have the concentration more than 10 to 15. But now these two still have the concentration around 10 to 10. So that's actually 5 times concentration lower compared to the silicon. So wide bandgap material has a lower intrinsic carrier concentration. We can observe from here, it's probably like 5 times older than the silicon. And therefore, this can give us advantages that we have very low semiconductor electric current at a high temperature. And that's good for the high temperature application, because in the certain application environment, we need our semiconductor electronics working in a very high temperature. So for example, here is some high temperature electronics application. For the one who close to our life, for sure is automotive, especially like an electric hybrid vehicle here. So usually for the EV car, the temperature can be up to 150 Celsius degree here, and that's why it's already mentioned that it's promising that we can use a wide bandgap material here. And now that's not only in the paper publication. This is a paper published in the 2000 preceded of IEEE in the 2002. That's almost 20 years ago. So 20 years ago, it's already there's a prediction that for the EV car, we need to use a wide bandgap material like a GaN or silicon carbide. The pure estimation is come from the equation. It's come from the pure semiconductor series here, the pure semiconductor analysis. But now this is no longer as a estimation or series anymore, because if you look at for the Tesla Model 3, there's a silicon carbide based inverter inside. So that's kind of how the semiconductor in the series right now is become the real life electronics applied in our daily life. And this is not only as a regular application, it's a very unique application. That's why the EV car right now can become the technology that completely like the very popular in the market, because we need a certain very unique semiconductor technology. So this is just a case that this paper published in the 2002 is already made estimation that we need a certain high temperature electronics and a role of a wide bandgap semiconductor. And based on this graph, they make this estimation. And how this graph come from? It comes from the very fundamental, very basic equation here. And now in the 2000, this car, I think no doubt, that's a Tesla EV car, has already in the market like more than like 10 years. Not only for the Tesla, in the every EV car now, like the Porsche, like the every lots of EV car, they all adapt to use the silicon carbide inverter. So that's one of the example. Of course, for high temperature, there's still some that might be interesting that you have to know. For example, the application in the space. That's needed because when you try to make the electronics in the how we say the space explorer vehicle in the different like the space region, actually the different the different planets in the space, they have extremely different temperature, not like the every planet in the space has a temperature like Earth. So usually they may have the temperature varies from the -200, even can be up to 500 Celsius degree. So that's why you need to have the high temperature electronics. But also on the Earth, if you consider like a deep well drilling, that you try to have this technology for the like oil and gas industry. This also the temperature can be go up to more than 200, 300, and that's why we need to have the wide bandgap material here. And this also a very nice example that I just want to illustrate that those basic equation, sometimes this equation is look very normal and nothing special, and most of you might once you learn this equation, you found that the calculations might be very complicated, but after a certain moment that you found that you will forget this equation. But in my opinion, that this still very useful, because if you understand this equation, you actually already can read this paper. This is published in IEEE paper. You can already fully understand how this paper try to describe, because it's all come from this basic equation here. So in general, if we have the lower intrinsic carrier concentration here, that can, if we lower Ni, so that's a good, because we can have a lower leakage current. And since we also mentioned the space explorer, so it's interesting to know that actually this is not like just pure like the paperwork that we all talk about on the academic paper. It's really the certain technology that we already demonstrate and then put in the space. So if you look at for the NASA's page, this is NASA has a research center called the Glenn Research Center. And in the NASA, this page, they actually specify all the technology they develop for the space application. And they have the one dedicated space for silicon carbide, electronics, and sensors here. So the NASA Research Center is developing silicon carbide as a material for the advanced semiconductor electronics device application. So if you're interested, you can look up. And also want to share one more thing, that this also is a technology that's still ongoing, and then you can still find out that there's more and more related publication published in the last 5 to 10 years. So this is paper published in the IEEE deal 2017, and this is these guys are all come from the NASA. So they are not only like develop the technology, they sometimes also will write the paper. So these are the paper come from NASA, and they demonstrate a 4H silicon carbide digital circuit above the 800 Celsius degree. This is because in the certain ambient that it needs have the in a certain ambient out of in the space, actually you will reach the condition that beyond 500 Celsius degree. So they want to demonstrate the possibility that the semiconductor device still functional in the extreme temperature. So since we also find out this paper is good, like we can also use this paper as a good teaching material that help us to understand how the academic writing and how this paper structure look like here. This paper, as I say, is written by the NASA. They are all Native Americans, so I think the structure they use, the grammar they use, how to organize here is very useful for us to understand how the academic writing here. So as I say, if you look at this paper in detail, still we always starting from the introduction. So introduction, you can find out that what the introduction say. First of all, wide bandgap semiconductors theoretically enable hundreds degree increase in the semiconductor integrated circuit ambient operating temperature over silicon, and development silicon carbide or 3,5 nitride IC for temperature larger than 500 Celsius degree have been reported. So you can see it's always from the beginning, it's just a general overview. If you don't know how to write a paper, in the beginning, just remember that we will write a very rough overview of how that the typical status of one technology that you are working on. And we'll start to mention, this is a general overview of the background history, but also we will start to put some more of the review in the recent development. So then you usually all use the term recently. That's also the term very often used in the paper writing. Recently, silicon carbide junction field effect transistor JFET IC with a 2 level of interconnect have been started consistently demonstrate with a longer hours operating at a 500 Celsius degree. Which is a significant step towards beneficial into new application, including the jet engine ground test, Venus service exploration. So that's actually also another review, but that's a review in the more recent result here. Because when we try to illustrate that our certain advantage in a certain paper, we always starting from the general overview, and then we'll start to mention that what's the recent, like the up-to-date technology development. But still, although there's some recent development, but still something is not perfect. We still need to find out some issues and we want to address them. That's how this is important in this paper. So therefore, we still will try to propose some issues here. So the ability to operation stress semiconductor device at temperature have higher than application have proven crucial to reliability assessment and qualification of IC. So still there's a general issue related to the reliability of this silicon carbide device. And second issue is expansion of IC operating temperature can be expected to span new application not presently have here. So in here, how this introduction organized. First, you have a general overview. You have the overview just mentioned in the recent progress. But still, even for the recent progress, there's some issue. The first one is a general issue that they have a reliability issue. And second one is there's a specific issues here. And therefore, that's also another. So the third and fourth will be the motivation of this study, because this is something that still not perfect in the past study. And then that's why this paper want to address this issue. And therefore, in this paper, he also mentioned that we previously report the short-term 150 hours operation of the silicon carbide JFET at the 727 Celsius degree. That's how he reported. But in this paper, definitely want to do something more here. So therefore, that's the purpose of this work. Here we report operating test of a similar silicon carbide JFET IC, but at temperature up to 961 Celsius degree. So you can see that as an introduction, what they try to say is that, okay, there's already many people think that the silicon carbide is very promising for the high temperature, but in the previous work, it's only up to 500 Celsius degree. So that's how the previous work reported. And in their previous work, they also reported a condition slightly higher than 500, that's around 700 Celsius degree. But now in this work, they want to put an even higher temperature to see how this device can survive or not. So that's why they target as more than 950 Celsius degree. So that's exactly the same, the very typical style how we actually illustrate the introduction. So it's good to read this introduction and then to understand how this academic paper organized here. So of course, the detail of this paper we won't mention in this class, but at least if you have a knowledge of this intrinsic carrier concentration, you have a knowledge a little bit about the band gap. I think if you read this paper, you can only with introduction part that you already can guess the contents inside, whether it fits your need and whether you would like to keep reading or not. Because if this is not exactly what you need, you can just completely skip this paper. But at least this introduction already gives us enough information to decide that whether we should continue to look up and read later, read this paper in details or not. Okay, so we will take a break. We'll come back in 10 minutes later. Today you have to submit your homework, so you can put your homework in one of the tables. Yes.
About this good homework. So I see that you say it's not really simple or not. But can we write it first and then scan it?
Yeah, sure. No, I prefer to print out. It's not allowed to submit online. You have to print out.
No, I mean so.
Also, it's all print out and delivered to us because that's more convenient for us right here. Oh, really? Okay, then I will check out later. Okay.
老师，我看那个第一单的作业，我以为是这礼拜才要写，那我今天没办法交，可以今天下午再交去给助教，我等一下写。
OK，好，谢谢啊。
对，对，正常是只要除以这个 cubic A3这边就。
对，没错。
对，但是我找到这一行，它奇怪，它除了求这个之外，它另外还把真正的这个把它算出来，然后再去扣掉它，这个再去减掉这个，就是说，它好像是把那空隙扣掉。
你可以先算算看，因为我要就去变的办法，就可以忘记你的那个。
那本来正常应该除以 A 方就对吧？那它确实这样子。第二个问题是，这一种模型如果要画它的方向，
对，
是大概画还是？
大概画，就是一个当然是可以，尽量画就是你，表现。重点是这个方向是这样上的，对，你不可能这个手画是没办法画的。
我以为要真的要修出发线，
不用。
OK， 谢谢。
Okay. Before we continue, so it has been, I think this is maybe 4 or 5 weeks already since the starting of this semester. So I would like to take a roll call for all of you. Also good to let me know, just at least I can pronounce your name correctly. Probably I can recognize you. So if once you hear your name, just answer me. 丁惠慈。刘燕云、郭品轩、王威志、蔡庆辉、黄伯君、何一凡、吴泽威、Honey。I think this is an international student, Hani, H-A-N-I. 哈扁、常佩姐、拉伟、骆美轩 ，I think this is also international. 胡凯军。阮灵芝、黄玉哲、周燕婷、Yvonne、I think I have seen him. 刘博威、史淑慧、吕彦和、夏君熙、姚新宇、安雅、Anna、安慕汉、张佑祥、张文新、张义良、艾丽莎、曾子豪、李佩如。What's your name? Okay. 李云哲、林志勋、林博宇、林玉清丹、柯若妮、梁策、杨子贤、汪潘爱玲、沈伯君、法瓦兹、洪怡珍、潘林远、王玉祥、王佩荣、范江义安、范养浩、蔡廷虎、苏玉宁、许廷玉、陈怡贞、陈映如、陈玉安、马培新、高瑞成、黄宏玉、黄俊杰、 黄俊杰、黄永山、吴文轩、卓宇腾、王正照、郑彩妮、陈瑞宇、乔永章、宋欣雅、李玉琪、林冠霖、林佑新、杨祥超、苏新友、唐秋吴、张成佳、黄子婷、艾香林、肖玉婷、吕浩宇、陈鹏谋、黄成颖。Okay, so let's continue. So the next is we also will be interesting to put some understanding on the intrinsic Fermi level position. So when we talk about the intrinsic semiconductor, it's a condition that a piece of the material both have the same electron and hole concentration. So therefore, the electron and hole concentration are equal. So that means this equation can be show me here. We have the NC exponential KT EC minus EFI is equal to NV exponential KT minus EFI minus EV. Because right now we consider for the intrinsic Fermi level, so that means this is intrinsic Fermi level. And once we consider these two will be equal, then we can have this equation out here. So actually, the intrinsic Fermi energy is not exactly in the middle between the conduction band and valence band, because there's a additional term here. So that means if you try to plot this is EC and this is EV, and the exactly middle between the conduction band and valence band is how we call the EMI gap. So that would be here. But if you try to calculate the EFI, actually it's not exactly just in the half of EC and EV. It's actually there's the term in here. So that means in reality, the EFI can be here. So the EFI minus E middle gap, there's a shift like here. That depends on effective mass. Okay, so next we will start to talk about the dopant atoms and energy levels. The intrinsic semiconductor might be interesting, might be an interesting material, but real power of semiconductor is realized by adding small control amount of specific dopant or impurity atoms here. So we can add a small amount of the additional and try to change the electrical characteristic of our one piece of semiconductor material. So the doped semiconductor, that's how we call as a extrinsic material. So in the left hand side, you have the piece of the silicon and without any additional doping and atoms. So that's how we call this as a intrinsic here. But now if we try to have additional atoms, for example, if we have a silicon here, so now if we put arsenic, we dope the arsenic in this material. So the arsenic has 5 electrons in the outer shell. So that means you have 1, 2, 3, 4. But also there's a additional 5, can be the 1 as a free electron here. So that means we can make this material as a N-type, because right now we have more electrons than the holes here. And since this is a material that dope with additional dopants, so that's we call this as a extrinsic material. So now consider adding a group 5 element such as phosphorus as a substitutional impurity. In here we use arsenic. The group 5 element has 5 valence electrons. And then 4 of these will contribute to the covalent bonds with silicon atoms, and leaving the fifth the electrons loosely bound to the silicon atom, so that can act as free electrons. So as I say, adding control amount of dopant atoms, either donor or acceptor, creates a material called an intrinsic semiconductor. And an intrinsic semiconductor will have either the case with full of the electrons, or the case with holes. So in the left hand side, this is a case that's how we already draw, whether you have the arsenic and you have a 5 and you have additional 1 here. So that's a N-type. And because there's an additional electron is donated by the arsenic, so that's why we also call this as a donor. And if you consider the case, like the right hand side, still you have the so right now, if you put a boron here, and boron only have the 3 electrons in the outer shell. So that means you will leave an empty of the one place. So this will become empty, and that will become the whole. So this empty means that there could be some additional, this can be the place to accept the electron from the other place. So that's why we call this as an acceptor. Because we have the empty place, so it means we can accept the carrier from the other place. So this is a material that exhibit the p-type property. So that's we call this as a p-type material. And when we consider the donor impurity atoms, so the donor electrons can be elevated into the conduction band. And leaving behind the positive charge phosphorus ions. And the electron in the conduction band can now move through the crystal and generating a current. And while the positive charge ion is fixed in the crystal, so the resulting material referred to as an N-type semiconductor, and N is for the negatively charged electrons here. So what does this mean here? This means that if right now you have the discrete donor state like here, so once we put the additional atoms, we also have to consider the energy level of these atoms here. So then we can use this one to refer to the energy level of this additional donor. And if right now we have EC and EV, and because we put the additional donor here, so therefore the donor state is shown in here. This is the energy state for the donors here, and the donor electron can be elevated into a conduction band. So that means this can jump to the conduction band and leave behind the positive charge ion. So once the donor electron jump to the conduction band, and therefore the positive charge will left behind. So this will become like here, positive charge, and now we have the negative electron in the conduction band here, and the electron in the conduction band can now move through the crystal and generate the current. So that means this part can move in the crystal and become the current here. So that's how these two describe here. That's how these two describe this behavior here. Then the approximate energy required to elevate donor electron into a conduction band. This energy is referred to as ionized energy. So that's this one. The small gap here is what we call the ionized. It's what we call the ionized energy. So that means this is the energy that the electron needed this amount of energy to jump across the conduction band, jump to the conduction band. So that's how we call this as the ionized energy. So if that means if this gap is small and small, that means our ED is close to our conduction band, and you will have more electrons will be able to jump to the conduction band, because then if you have ED here, that means the electrons getting more easily to jump to the conduction band and become the current. So therefore, if the ionized energy becomes small, then electron in the conduction band is increased. So that's a very important conclusion. So right now, we not only have the conduction band, valence band, we not only have a Fermi energy, but once if we dope additional atoms, we have also consider the discrete donor energy that come from this additional atoms here. So this gap is how we call this as ionized energy. So that means the additional atoms, if they want to contribute the current, first they need to overcome this energy and jump to the conduction band. So therefore, if this ionized energy is smaller, that means more electrons easily jump to the conduction band and become the current here. So that's why if the ionized energy becomes small, the electron in the conduction band is increased. And the same things can also be extended to the one of the acceptor. So we have the here is a acceptor state. So this electron position can be solved as a whole in the semiconductor material. So again, we have the acceptor state in here. So EC, EV, and we have the acceptor state. We have acceptor state EA here. And also, the hole can move through the crystal. So once we have this across this gap here, the holes can move through the crystal and generating a current. And while the negative charge borons are fixed in the crystal, so you have the fix in the crystal, but now you can actually generate a current here. So the type of semiconductor referred to as a p-type material. And P is because for the positive charge hole. That's why we call that this is a p-type material. And since we talk about the concept for the ionization energy, so we have ionization energy for the electron, but we also have the ionization energy for the hole. So that's ionization energy for the holes in the silicon material. So therefore, in the summary, if you consider this is a typical ionization energy in the silicon and germanium with donors with acceptor here, and therefore that's generally like it's very the value is very small. So that means that the hole or electron are easily jump to the conduction band or the valence band and generate the current here. So let's say if you consider the silicon case, this is ECEV here, and then we have the EA, that's a acceptor state. That's the acceptor state here. And in the case if we consider the boron and the ionization energy is only 0.045 electrons here, but this value is very, very small. So that means if we try to dope, for example, 10 to 20 of the boron, actually the whole concentration also will be approached to the 10 to 20, and that means we have the 99% of ionized. So that means whatever you dope as a extrinsic oton, additional oton, almost 99% can contribute to as a whole and in the end to contribute for the current here. So this is a case for silicon. So in the silicon, this concept is important, but actually it won't influence a lot on the characteristic between the otons and also the ionized one to contribute to the electron holes. But the problem is that if you look at for the other materials, for example, if you look at for the gallium nitride material here, we have also the EC and EV here. But the problem for the gallium nitride can be, if you want to make the p-type material in the gallium nitride, actually that is not that easy, just like the silicon case. It's very complicated. This is because the EA for the p-type material in the gallium nitride has relative large ionization energy. That means the gap here is large, sometimes larger than 0.3 electron volt here. So how do we determine whether the energy is small and large? That need to always to refer to the silicon case, because silicon case is 0.045 electron volt. But now this is almost like 10 times larger, so 0.3 electron volt for the ionization energy is already very large here. So if the ionization energy is large, that means not all of the dopant here in the gallium nitride can contribute the holes here. So for example, if you dope for around like the still, for example, 10 to 20, but probably it's less than 10% ionized. So that means that you only have 10% of your dopants can contribute the holes, that become the whole concentration, become the whole carriers in the semiconductor. So that's a difference between the silicon and with other non-silicon materials. Most of the non-silicon material has all the issues that it has a large ionization energy. That means it's difficult to make as a very efficient N-type or P-type semiconductor material. Okay, so this one is something that we also have been already discussed in the end, that how do we calculate the electron and hole concentration. So just let's quickly review again. So it's always, we're starting from the conduction band, EC and EV. But now, if in the previous case, we always discuss the intrinsic material. Intrinsic material, that means our electron and holes concentration are equal, and that means our EF is almost in the middle. Of course, it's not exactly middle, but it's almost in the middle. But how about if our EF right now is close to the conduction band? And how do we use this equation to further estimate the electron concentration? But the concept is the same. If we have EF here, and let's just do this state by state. And next one, still the same. We will plot the in here is a DC, but in the previous slide, what we talk is a GC. So in general, it's the here. So we have the allow energy state in here. But right now, because our EF is become shift to here, so that means your previously the Fermi-Dirac distribution also have to shift upper, because right now you in the past we assume in the middle, so we have a graph like here. But now you shift to here, so that means your graph will be more like here. So that means right now you have this. So, and then this is our, and what does this mean? This means that because this shift up, that means the overlap region is become larger. And if we have the overlap regions become larger, so that means you have a larger area. Larger area for the electrons. And your hole now is smaller. So right now we have the material that has higher electrons compared to the holes. So that's why this is an N-type material. So again, this is just another way to illustrate the concept that how we determine the electron holes. And I believe the results here are also very consistent to what we already described. Either you use pretty like the analytical equation, because the gap between the EC minus EF is smaller, so your exponential minus this term is higher, and therefore that's why you get a higher concentration. Or you can just simply use this graph, because this Fermi energy is shift, and that means your Fermi Dirac distribution also shift up, and therefore the overlay regions become larger. And once your overlay regions become larger, you have a larger electrons concentration than the holes. So we still get the same conclusions. So that's exactly the mention here that how actually the previous calculation, when we consider the GC, the allowed energy state distribution times the Fermi Dirac distribution, how these two combine in the end to help us to calculate the equilibrium electron and the hole concentration, and then the overlap region here. It means this is electron concentration. This is a hole concentration. And if EC minus EF is small, we have a two ways to understand. One, either come from this analytical equation, this becomes smaller, that's become larger, or this EF shift upper. So if you shift upper, that means you have a larger overlap region compared to the holes. So if EC minus EF is smaller, that means the electron concentration will be dominating the whole materials here, and that becomes the N-type. So that's will become a very important conclusion, because in the future, when we draw the band diagram, we will no longer to draw this. We only draw EC, EV, and EF. That's all. So in the later discussion, we only use these three lines, try to illustrate the carrier concentration and carrier transport here. And that's actually is based on the conclusion come from here. Okay, so here's something more like the calculations here, because we have introduced several terms. For example, intrinsic carrier concentration, intrinsic Fermi energy. So therefore, we can do some interesting calculation here. So we have the NC N0 is equal to NC exponential KT minus EC plus minus EC minus EFI plus EF minus EFI. And therefore, this term can be also rewrite as the NC exponential here. KT minus EC minus EFI exponential KT EF minus EFI. So this one is become this one as an intrinsic carrier concentration, where you have EC minus EFI. So in general, just try to put the sum of the defined parameters that we already have of the intrinsic carrier, intrinsic Fermi energy inside this equation. And in the end, you can try to calculate the intrinsic carrier concentration equal, Ni is equal to NC exponential EC minus EFI. So furthermore, there's some additional calculations here. So as I say previously, we already have this one. N0 is equal to Ni exponential this one. EF minus EFI over KT. So that's a thermal equilibrium electron concentration. And also we have a P0 is equal to Pi exponential minus EF minus EFI over KT here. And if right now N0 times P0, if we try to do this calculation, that would be equal to NCNV exponential minus EG over 2KT. So that's something we have already derived before. So this is some equation that we can when we talk about the band gap. But right now, this times this and this can be cancelled, and therefore this will be also equal to this one. And because this is intrinsic carrier concentration, so Ni is also equal to Pi. So that's becomes Ni squared here. So that's usually what we call this as a max action loads here. So I believe everyone in here should be very good at the mathematics. So it's just a matter with a little bit time for you to digest these calculations. So it should not be too difficult, just a simple mathematics tricks here. An intrinsic semiconductor in thermal equilibrium does not, strictly speaking, contain an intrinsic carrier concentration, although some thermally generated carriers are present. The intrinsic electron and hole carrier concentration are modified donor or accepted impurities. However, we may think of the intrinsic carrier concentration Ni simply as a parameter of the semiconductor material. So we can just Ni is usually considered as just a typical material properties here. Different material has a different Ni in the end, that's also leading to the different electrical characteristic. And when we consider the extrinsic semiconductor, there's also one consideration that we need to be aware of is how we call the degenerate or non-degenerate semiconductors. So degenerate and non-degenerate, the concept is very simple. What does mean the degenerate semiconductor? That means if right now we have the EC and EV as shown here. There's a chance that actually we dope too many extrinsic dopants, and these too many extrinsic dopants make the Fermi energy actually is above our conduction band. So that's how we call as a degenerative dope N-type. So let's just go through the text together. When the concentration of electron in the conduction band exceeds the density of state Nc, the Fermi energy lies within the conduction band. This type of semiconductor is called a degenerate N-type semiconductor. So that means right now, EF is not in the forbidden band gap. It's actually inside the NC, EC. So that's what we call as a degenerate. But the idea is just if once you dope too many additional altons here, and that can be possible that this EF, as you know, in the beginning the EF should be in the around the middle. Once you start to dope become N-type, then EF will start to moving toward the NC. But there's a chance that you dope too many, so the EF is already above the EC. So that's we call the degenerative dope N-type. And the same thing is also possibly in the case of P-type. So if we have EC and EV here, right now, if we dope too many P-type altons here, so our EF is below EV. So when the concentration of a hole exceeds the density state of NV, so that's how we call this a degenerate P-type semiconductor. So the concept is the same. In the beginning, we always has a EF around the middle, but now if we start to put some of the P-type altons here, the EF will start to shift toward the EV. So that's why we consider that's a P-type. But there's a chance the EF can be below the EV because of the doping of the P-type is too many here. And that's how we call this as an extrinsic semiconductor. Okay, so probably that's quite a lot for today. So we will stop here and then we'll continue for the next week. So see you all next week. And remember to submit your homework here. And also we have another new homework that you need to submit in the next week. Also with paper, submit in the paper version. If you type it, you can just print it out. Okay? So if you have any question, just let me know and see you next week.